Okay, hi guys. First of all, you'll have to forgive me for sounding so stuffy. I'm still fighting this cold. We're going to cover section 5.6, the fundamental theorem of calculus, which is such an awesome thing. Now, I'm going to probably put a link to a video for Khan Academy for you to actually see the proof of the fundamental theorem of calculus. And we're just going to pick this lesson up because it's a little bit long. Right here, just applying the use of the fundamental theorem of calculus. So I do want you to watch the proof of it to know exactly where it evolves from, just so you can have an appreciation for it. But for our lesson, I'm going to cover um, the application of it. So this is just a statement if you want to pause it, and these definitions come straight from your textbook in section 5.6. But the fundamental theorem of calculus, so f is a continuous function on a closed interval a to b. Then if the function g is defined by this value right here, then for every x in the closed interval a to b, g is an antiderivative of f on a to b. Okay, and then for part 2, if f is any antiderivative of f on a to b, then we're going to have this value. When you evaluate it, it's just going to be the f of b minus the f of a. Now, the result of this will just allow us to evaluate definite integrals using the antiderivatives of f of x without taking the limit of the Riemann sum. So all that work we've been doing in those previous lessons, this fundamental theorem of calculus is going to be a great tool for us. Okay, and this is just a corollary in your textbook, and that's just saying the same thing. If we take the antiderivative and evaluate it from b to a, we'll be able to find the area using the f of b minus the f of a. Okay, kind of a restatement. I also want to remind you about some properties, and we talked about the properties of this right here, if a and b. Remember, if the order of your limits of are right here are in the reverse order from b to a and a to b, then remember a negative sign comes out front, and I showed you an example of that in the last class period. So if the lower limit and the upper limit reverse order, we have a negative out front. We said this value by definition, the previous definition is the, in this case would be f of a minus the f of b, because it's the upper limit minus the lower limit evaluated there. And then you would just distribute that out and reverse the order, so it's just our f of b, capital F of b minus capital F of a. That's just reiterating the property. We also talked about this property previously. Of course, if this is a to a, then you would just have your capital F of a minus your capital F of a, and of course that's just going to be equal to 0. So those two should be a little bit familiar to you. And we're going to start off by this first problem and evaluate the integral here. So let's go ahead and do that one. I want you to take the antiderivative of this and then evaluate it right here using your upper and lower limits. Pause the video and see if you can do that, and then check your answer. Okay, just remembering that the fundamental theorem of calculus provides a method for us to evaluate this definite integral using antiderivative. So we're going to take the antiderivative term by term, so that's going to be x to the third divided by 3 minus 4x squared divided by 2. Now, as we progress, I'm going to go ahead and simplify these as we go, but for this first one, I'll write all of the terms down and then we'll simplify. And this is evaluated at 4 and 1, the lower limit of 1 and the upper limit of 4, excuse me. Alright, let's simplify this. So this is just going to be x to the third minus 2x squared minus 3x. Okay, and we're going to go ahead and evaluate those. So our first one is everywhere there is an x, we want to plug in 4. Remember, we're going to do f of b minus the f of a. So if this is our a and this is our b, then we recall that we're going to be evaluating f of b minus f of a, and that's from our integral right here. Integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. So we are now working on that. So our f of b, let me put that in one color. So that means f of 4 minus f of 1. So our antiderivative is just this value here, this function, and now we want to plug in 4 everywhere that there's an x. So it's 4 cubed minus 2 times 4 squared minus 3 times 4. Okay, that's the first term. And then we want to subtract the second term, which I'll do in red. This is our f of a term. So everywhere there's an x, we want to put 1. So it'd be 1 cubed minus 2 times 1 squared minus 3 times 1. Okay, plug this in, we'll simplify this. Let's see if I can get a little more room here. So that's just going to be 4 cubed is 64 to the third minus, let's see, 4 squared is 16 times 2 is 32 minus 12. Over here I'm just going to have 1/3. 1 squared is 1 times 2 is just 2 minus 3. So I have, when I simplify this, I got negative 68 thirds minus a negative 14 thirds, which simplifies to negative 18. So check that, make sure you agree. Okay, let's see our next example, evaluate the integral, similar idea. I want you to actually try this one all the way through on your own now that you have an idea of what we just did. I'm going to suggest you do some rewrite steps here. Go ahead and move this to the top and then write it as an exponent before you find the antiderivative. And then I would start on your evaluation fundamental theorem calculus. Okay, before we get too far, first of all, I just wrote my theorem up here. Second thing I told you to do was just rewrite. Let's rewrite this problem algebraically. We have this, we bring this to the top and rewrite it as a negative exponent. Now, we still want to do a little more algebra to that. I went ahead and multiplied this times each term in here, so I distributed it out. The note on the side is t to the first power times t to the negative 1/2. Remember, when you multiply like bases, you add the exponent. So that's where this t to the 1/2 comes from. So that's that side note on the algebra there. And then negative 3 times t to the negative 1/2 is just this term. So we're finally at the point to where we're ready to take the antiderivative. And when you get t to the 1/2 plus 1 would give us t to the 3/2 divided by 3/2, but remember that would give us 2/3 out front minus, now negative 1/2 plus 1 is just going to be 1/2 divided by 1/2, which would just be times 2. So that's 3 times 2, which would be 6 t to the 1/2. And that's going to be evaluated from our limits, the upper limit of 9 and the lower limit of 4. So let me do this simplification on the side for you. Okay, so just this term right here, I pulled it over here to the side. When I say t to the negative 1/2 plus 1, that's just going to give me positive 1/2. So then when I divide by positive 1/2, it just means multiply by 2. And of course I have this 3 that's just already there. So negative 3 times 2 is the negative 6 t to the 1/2. Okay, so basically I filled in our function, and the first one we're going to plug in is going to be our f of b. So we're going to evaluate this at 9. That's going to be our antiderivative evaluated at 9. And then over here we'll have our f of a, which now I want you to go ahead and calculate this out. And when I simplify this term, I will get 18 minus 18. And then over here, I get this term will simplify to 16 over 3, 16 over 3, and then this side is 4 to 1 half times 6 looks like. That simplifies to 12. Now that's 18 minus 18 just gives me 0, and I subtract my term on the right is going to be negative 20 thirds. Okay, so minus, don't forget your minus and negative there, so this entire problem will, the solution will be 20 thirds.